Hello everybody, welcome back. Today we're going to talk about coordinating between fuses. So one of the principles of our distribution system is that we want to affect the minimum number of people possible when we have a failure or a system fault. So to this end, we've got a lot of sectionalizing devices or devices which will break our system into smaller chunks spread out throughout it. If you take a look at the circuit that we've got laid out below here, you've got your source, and so this could be back at the station, and this would have a breaker and a relay there, providing nice protection. And you'll have this main trunk line coming out of there. And that main trunk line, they often run down, um, you know, good sized roads, right? So these aren't the ones you see running down side streets usually. These will be on a major thoroughfare or at least near one. And as a result of that, these tend to not have a lot of trees growing up close in between them because they tend to be in more commercial spaces. And you'll often find you've got your critical customers sitting on that main trunk line, right? So that could be a hospital or a school or a fire station or a police station or town hall. Um, so you've got these customers and you really want these guys to stay on. But because of the architecture, and where you have your lines, you're also going to be hooking up, a little residential cul-de-sac here or a residential subdivision. And you take off down the main line and you turn onto the side street into the residential area, and all of a sudden, the nature of the area you're in changes. There's trees all of a sudden. There's squirrels. Sometimes those trees are right up into your power lines. And so if you're going to have a failure, your failure is more likely to be in here with the treed area than it is to be out on the commercial thoroughfare where you're done not to have so many trees or other things in proximity to your lines. So, to that end, what we want to do is whenever we have a lateral, whenever we break off that main branch of line and head into some place where we're more likely to see a failure, right? Because we're going to have more stuff, trees, in proximity to our lines. What you want to do is at that tap, what you want to do is install a fuse right in line here so that if you do end up with a problem down here, the fuse can operate and now all of this stays on and only these guys who were affected by the fault, right? Or if you get a fault in the cul-de-sac, you take the cul-de-sac out, these guys go without power, but the critical customer stays on, and this subdivision over here, which didn't have a fault, power stays on over there as well. And this is that idea of segmenting. And we've got a number of devices that'll do that for us, but one of the main ones, and we put them everywhere because they're very cost effective for what they do, is we use fuses. But with those fuses, we have to make sure that those two fuses are set up to play nice with each other. If we take a look here in our cul-de-sac, we've got a fuse here at the corner when we turn, but there's also fuses protecting our transformer. If we end up with a fault on one of our secondaries, we want to make sure that it's the transformer fuses that operate instead of the fuse at the road. So these fuses and back here at the source, the settings in that breaker all have to be set up in such a way that the furthest downstream device is the one that gets to operate. And so when we're talking about that, what we use is this idea of protection zones. So this is a protection zone would be the set of lines and equipment that a fuse or other protective device, could be a relay, breaker, recloser, whatever, So your protective device is set up to operate. So if we think about our diagram here, we could come off a recloser, or this could be the breaker depending on the size of the station, and that's going to go and it's going to protect that main bus all the way out till we get here to that lateral tap, and then we're going to set up a line fuse. Now once we're on the downstream side of that line fuse, once we're down into this region in the subdivision or down in the cul-de-sac, we don't want the breaker or the recloser at the station to be operating anymore. Now we want our line fuse to operate. So we have another protective zone here. This is the set of equipment that our line fuse is responsible for. So we take a look on our diagram, and we would say the line fuse is responsible for this section of line here in the cul-de-sac and would be responsible for this whole section of line here in our subdivision. And then we get to the transformer. And our transformer fuses, they're responsible for protecting the transformer itself and the entire secondary network that that transformer is attached to. So if we had a fault on this transformer secondary, we wouldn't want to take out the entire subdivision because our line fuse operated, and we certainly wouldn't want to take out the whole circuit, including our critical customer, because we operated our protection back at the station. So this is the idea of protection zones. And when we're talking about how far a device goes, we use the term reach, right? So your recloser or your station breaker should reach out to, but not past, your line fuses. Your line fuse should reach out, but not past your transformer fuses. Your transformer fuses should reach all the way to the end of your secondary network. So when we're talking about fuses or protective elements in series, and I'm just going to call everything a fuse for the purpose of this argument and our lecture here today. So the idea of a protected fuse could be a protected recloser or a protected breaker, but we're just going to go with fuse for the sake of simplifying the discussion. So we introduced the concept of a protecting versus a protected device. The protecting fuse is the one you want to operate. All right, so this is the one that operates. The protected fuse, which is the upstream fuse, that we do not want to operate. Right, so if we get a fault down here, right, this is our subdivision or our cul-de-sac, we get a fault downstream of those lateral tap fuses, we want the fuse down here to be the one that operates, not an upstream device closer into the source. Now, if we get a fault here, obviously this fuse and this fuse can't do anything about that. All right, the fault is upstream of them. So it's going to be, this will be the most downstream device to see the fault current. So this becomes our protecting device, and if whatever upstream protection exists would become the protected device. So these are some of the terms that we're going to need to know. We're going to have to understand reach. We're going to have to understand protecting and protected. And if you can keep these term and the word sectionalizing, if you can keep those terms straight, that's going to make this next section pretty easy. So, if we're talking about protecting and protected, obviously, if our upstream fuse is being protected from operation, that means that we don't want that fuse to operate. We don't want the element to melt. And I'm going to extend that concept just a little bit and we're going to say, I don't want it to be damaged at all. Now, there's a little bit of complication that arises because our fuses can be subject to the upstream fuses and the downstream fuse, protecting and protected, are going to have some differences. One of those fuses might be in the shade while the other one's baking in the sun. One of those fuses could be in an electrical room in an air-conditioned building, while the other one could be baking in the sun. Right? So there could be big changes, or the reverse could be true. One of those fuses could be in a heated electrical room while the other fuse, your upstream fuse, is freezing in the cold. So there's going to be differences that the upstream and downstream device could be experiencing in what sort of temperature they've got and they're experiencing. So another thing that you're going to run into is electrical loading, right? So the downstream fuse that operates or experiences the fault, it might not have much electrical load on it, right? If the reason that the fault occurred is because a tree or a tree branch came down on it, or there was a motor vehicle accident, there might have been very, very little load on that downstream device. If we go back to our idea of the cul-de-sac, if this was a relaxed day and there wasn't, it's 25 degrees out and nobody's got their heat running, nobody's got their AC running, but it's fall, so all the pools are already closed. There's just not much electrical load happening here. But then a tree branch comes down in the wind and boom, fault. So this fuse really didn't, before the fault happened, didn't have much load on it. But at the same time, the upstream device back here at the source, this could have been a factory and they might be running full production. So even though this might not be seeing much electrical load right now, the upstream device might be seeing a lot of electrical load. Another thing that we have to keep in mind is manufacturing tolerances. So these fuses are made cheap, right? So they're mass produced and they tend to be bought, they're standardized across manufacturers. So they tend to be, a lot of times they're purchased from the company that's going to give the utility the best price because the utility buys a lot of them. So, did you get the fuse that was, sort of, the fuse element's a little bit short and the solder's not very thick, and so it's going to operate a little faster? Or, there's a nick in it, or so now there's a weak spot in the fuse element? Or did you get the fuse that had the chunky fuse element and they really gobbed the solder on it and they got a solder ball stuck in the middle and now that's acting as a heat sink and it's going to slow your fuse's behavior down a little bit. And then the last thing we got to look at is material properties. So silver and tin, which are the two materials that we make our fuse elements out of, when you heat them up right close to their melting point, but don't quite melt them, their mechanical properties start to be impacted by that. And so we have to look out for that. Stack all these things up, and what it boils down to is that we have to allow some margin. So when we're seeing this, this is going to be our protected fuse. And this is going to be our protecting fuse. And you can see that no matter where we operate this fuse, or most of the spots that we operate these fuse, the protecting fuse is going to be the one that operates before we get to the minimum melt of our protected device. So we can say that the protecting fuse is going to protect the upstream device, which is good. We can also say that the protected fuse does not reach past the protecting device. Now, this line here represents the amount of margin that we have to allow to make sure that all of these conditions are met. So this is our coordination margin. And this line is formed by taking the minimum melt of the protected device and derating it. So let's take a look at the elements that go into that developing that coordination margin. So we talked a little bit about ambient temperature. So ambient temperature, those curves, when we take a look at those TCC curves, the standard ones we've been using all semester, those are all calculated at 25 degrees Celsius. A nice warm day, but not too hot. Now, if the temperature starts going up, those fuse elements are going to be hotter. They're going to be closer to their melting point. If the temperature outside is cold, they're going to be further away from their melting point. So you're going to need to put more energy into them. And we can see that this affects the tin elements, or a fuse with a tin element. We see that that's affected quite dramatically, right? By the time we drop to minus 40, that tin element's going to be 20% slow compared to a silver, or compared to its base condition at 25 degrees Celsius. If we heat that thing up to 50 degrees Celsius, which is not that hard to hit if you're busy baking in the full sun, certainly the air around it wouldn't be that hot, but if you're sitting there baking in the sun, you can certainly reach these temperatures. You could see that you're going to melt at only 90% of your rating, so you could be going 10% fast. Silver, you see, is much less affected by that. And part of the reason the tin elements are so badly affected by temperature, whereas the silver elements are less affected, is that the melting point of tin is much lower than the melting point of silver. So moving up 100 or 80 or 90 degrees Celsius from minus 40 all the way to plus 50 is a much bigger percentage of the melting temperature than it would be for silver. So, silver links perform better when we're talking about big swings in ambient temperature, the kind of swings that we get around here or in this part of the world where we have a true four-season climate, right? Where we have cold periods in our winters, but our summers are still very hot. Now, electrical loading prior to the fault, the term we use for this is preloading. Our TCC curves have been developed assuming there is no preloading on the link at all. So preloading is going to get current flowing. Now, your fuse element is fairly small. It's designed to heat up to the point that it melts if you flow too much current through it. The side effect of this is if you flow just, some current through it, it's still heating up. It's still, becoming warm. It's just not coming so warm that it's going to melt, right? So if you take a look at that fuse, and if you're running that fuse at 100% of its rating, so you've got your 15 amp fuse link and you're running 15 amps through it, you're not really going to see a whole lot in the way of derating if you've got a tin link, but a silver link, which tends to have a much smaller filament on it, is already starting to lose, and that's down almost 10% of its melting point. So if you've got a silver fuse link, a 15 amp link should operate at 30 amps. But if you've been running that 15 amp link at 15 amps and you have a fault on it, that fuse link is going to operate more like at 28.5 instead of 30 amps. So it's going to start operating a little faster than you'd have thought otherwise. And you can see as you creep up past the rated values, they should operate at 200%. The melt time can get really fast, particularly with the silver, right? So those fuses get faster and faster as they are loaded heavier and heavier. Now, pre-damage is occurs when you heat up your fuse element almost to the point that it melts, but not quite enough to melt it. What happens is when you get that close to the melting point, the material properties of the element of the fusible element begin to change. So if you think about steel, right? You can harden steel, right? Or you can anneal, a process called annealing steel, which makes it really, really soft. The way you anneal steel is you heat it up until it's almost about to melt, and then you cool it down nice and slow. And if you do that, you're going to take your steel, you could take let's say a knife blade or a file. A file is a great example, right? So a metal cutting file or a wood rasp. This is made out of steel, and the steel is super hard, right? Because it's a cutting tool. So that steel is really, really hard. If you take a file and you heat it up just below its melting point and then you cool it down real slow, um, you'd probably be able to bend it with your hands when you were done. You'd have taken all of that hardness and much of the strength out of that steel. Now, certainly, if you were to, you could reharden that steel and give it its strength back. That wouldn't be a difficult thing to do. But the act of heating it up to just under its melting temperature and then giving it a nice slow cool down took all the strength, all the hardness out of that piece of steel. We see similar things happening when we have our tin or silver link. So if we get within 90% of the melt point for tin, 95% of that on silver, what we do is we start to change those properties of those fuse elements. And all of the sudden, we've damaged them. And typically what that means is that we've taken some of the strength out of that element, and this will cause us to operate early in the future. And so what you can end up with is if you get a lot of pre-damage events, and the longer you're in this, within this band, the more pre-damage that occurs. So although it doesn't take much to cause damage, it's very hard to model reliably. But if you get multiple of these pre-damage events, or you have a one that's really long, what can happen is the next time you have a high current, not a fault, but just a high current, that fuse that was previously weakened can let go. And it opens up, and now you've got an outage on your hands, and you're driving around trying to figure out what happened, and you're not going to find anything because the reason the fuse let go wasn't because there was a fault, which is what you're looking for. It was because it had suffered too much pre-damage due to high current flows. So what we have to do is when we're developing our protecting fuse settings, we have to make sure that we account for that pre-damage threshold on the protected device. So if we stack all of these things together, we can come up with a rule of thumb. And the rule of thumb states that what we want to do is we want to derate the minimum melt of the protect dead fuse to 75% of its rating before we, in order to allow that protection margin. So depending if we know exactly what's going on, we could have a really a liberal measurement might only be derating to 82%. Right, so if we knew that we'd never have a big temperature difference, both fuses are always going to be baking in the sun. If we knew that their electrical loading was always going to be the same, if we could guarantee they'd both always be tin or both always be silver, then maybe we don't need to derate all the way down to 75. Maybe we can leave ourselves a little extra margin and get those curves a little closer together. On the other side, if we know that all our worst cases are going to be realistic, right? There are going to be big temperature differences between them. There are going to be big loading differences between them. There's a good chance that we're going to have different fuse elements. Some are tin and some are silver. 75% might not be enough, and we might have to derate all the way down to 66%, which would mean we'd need a bigger gap in our fuse sizes to account for that. So, but lacking any additional information, if I just give you a circuit set and say, coordinate this, and we don't know anything about the specifics, what we're going to do is we're going to use 75% as our derating factor. So let's do an example. How do we calculate what the margin is? And here I'm asking for what's the maximum coordinating current. So the maximum coordinating current is this point right here. This is the spot where we no longer have our margin in place. So if we take a look here, we can see now our maximum clear time is on the wrong side of our margin line. So what we would say is we've lost coordination beyond this point. So in this case, we would track that down, and we would say that that occurred at just under 600 amps would be our maximum coordinating current. So in this case, we're in this example. So the example is, what's the maximum coordinating current if we took a 20T and a 65T fuse link? So what we're going to do, the way you solve this question is we have to figure out how to translate the minimum melt curve on the upstream or the protected device, the larger of the two, and we need to move it over this way so that the values are down to 25% of what we'd have had otherwise. So what we can do is we can build a table, and we can use that to translate our line over. So we're going to start out by reading some times and currents off of our graph. So we can start out, we're down here, we can see we're at 1, 2, 3, 4, 5,000. We're going to call that like 5,100 now. go to 0.1, and we're at 1,000, let's call it 1750, and go to 1 second. And going up through this lower section is pretty easy. You can just keep your points pretty well idly spaced. In through here, you might want to do a couple extra points in your table to make sure that you mirror that curve properly. So we're going to do 1 second, 1, 2, 3, 4, 500, and then this time, because we're going to hit that curve, I think what we're going to do is we'll go at, let's do one at 3 seconds, and at 3 seconds we are right at 30 amps, or sorry, 300 amps. Oops, we're running out of space here. There we go. We can keep going. And then maybe we want to do one at 5 seconds here. That's 100. It's around 100 and 230. And then we can do, oops, we can do 10, and that looks like 170, let's say, and we can keep going. What we're going to do is we're going to multiply this times our derating factor. Get that calculated. And we come up with a derated current And then what we're going to do is we're going to take these values and we're going to plot them back up here to form a line. So we start out at 37, or just under 38, somewhere around there. And then we're going to go up to 1312, somewhere around here, 382, and we're going to finish plotting all these points and we're going to connect the dots. And we're going to end up with a curve that looks like this. So the question we were trying to solve is, what was the maximum coordinating current? So we're looking for the spot where our coordination margin crosses the maximum clear of our upstream device. So we're looking for this spot right here. And we can see that that happens right around 3000 amps. So the answer to our question is 3000 amps. Let's do another example. So if we're given a transformer and it's got a 20T and a 40NX fuse protecting the transformer, if you take a look at this curve, these pairings of fuses, they should look familiar from last week between the 20 and the 40. And upstream, right, so at the edge of the road on the cul-de-sac where it turns off the main road, they've got a 65T line fuse. So now the question is, what is the maximum coordinating current? How big a fault can you get before you run the risk that your upstream device operates instead of your downstream device? If we're using a 75% derating factor, right? So we're going to draw in that derating line, and the question is, where does it cross, and where's that coordinating point going to be? So attack this one the exact same way that we went after the last one. You have to figure out what the 75% factor is on your minimum melt of your upstream or your protected device. So we're going to start out, we're going to build a table. And then we start grabbing our points. So 1, 2, 3. That's 1000. And we're going to keep building our table out, and we're going to spend some extra time and attention grabbing a few extra points along this curve to make sure that we get the elbow traced in properly. And we're going to take those and we're going to multiply each one down by 0.75 because that's our coordinating margin. We're going to get our derated currents, and then we're going to plot those. All right, so we'll get our derated currents. And then we're going to plot those guys back onto the graph. And we're going to build up our line. Right, so we end up with our protection coordination curve that we're going to build. And once our table is complete, it should look like this. So the question was, what is our maximum coordinating current? So we take a look. We know that it is not here. This is the first point we see things crossing. We know that it's not going to be here, because at this point it's not the current limiting fuse that is the one that opens first. The expulsion fuse is going to clear the fault before the current limiting fuse does. So the other point we could look at would be here. But in this case, we know that it's not the expulsion, that's not quite right either, because it's not the expulsion fuse that's clearing it, it's the current limiting fuse that's clearing it, right? We trace that over. The behavior of the fuse pairing for our clear is we're clearing here with the expulsion fuse, and then we clear here with the current limiting fuse. And we end up with something that looks like this. So in practice, this derating line doesn't ever cross our fault clear line, right? Because that's the path of our fault clear of seen upstream of the two fuses in tandem. So the answer is that these fuses coordinate for all currents. So there's no, it doesn't matter how big the fault is, these a 65T and the 20T40NX pairing will always coordinate. Whereas if we take a look at our first example, they would coordinate for faults under 3000 amps, but for faults over 3000 amps, there's the chance that the 65T fuse would overreach, and the 65T fuse could operate in addition to the downstream 20T, or the protecting fuse. So in this case, for numbers beyond 3000 amps, there's no guarantee that the 65T fuse does not attempt to reach past the 20T fuse, and we have a misoperation. We could also say that the 20T fuse would not properly protect the 65 for faults greater than 3000 amps. In this case, we're coordinated for all faults, no matter how large or how small. I hope that's been very helpful, and I look forward to continuing with you in the